lot to do today, so we want to move quickly. And in particular, I have a check-in that's not very complicated. So it's just asking a person to do the matrix vector multiplication operation in 3 cases. That's all. So just to move on here to the paper. So the matrix vector multiplication for the first one was 1, 3, minus 1, 5 by 1, 2. And it's not very hard. It's just how the parts combine, that's all. 1 times 1, 3 times 2, that makes 1 plus 6, so it makes a total of 7. For the next, minus 1 times 1, 5 times 2, so I think that's a minus 1 plus 10, so that's 9. Okay? So it's just arithmetic. A person can get the arithmetic wrong, but in some sense it isn't actually hard. The only other point here is with the 2 remaining parts of the question is that if you take a matrix that is 2 wide and try TWO wide and try to multiply it by a vector that is 3 tall, it just doesn't work. It's not defined is the sort of official title, but it simply doesn't work. You take the 1 times the 1, the 3 times the 2, and who is there to multiply by the 0? And sometimes people try to say something like, well, 0 is nothing, so it doesn't count. No, no, no. 0 is not nothing. Okay? So we've got an entry there. It doesn't matter whether it's a 0 or whether it's a 5,218. It doesn't matter. It is the wrong size. So 2 columns has to be 2 rows. Likewise here, single row just simply doesn't suffice. So for number 1, we gave the answer of what, 7, 9, the vector consisting of 7 and 9. And number 2 and number 3, you simply write not defined. That's all there is to it. Okay, very good. So so next we want to get into what we're talking about today because, like I mentioned, it's a long, lot of material to cover, and so I'm going to mostly do it as I often do when we have a lot to cover. I'm going to mostly do it by examples. So what we want to say is that these representations of linear maps can tell us an awful lot. So for starters, I want to show that no matter what matrix you write down, for example, the matrix 1, 2, 3, 4, it represents a linear map. So it's not the case that only some matrices represent linear maps. Instead, any matrix you scribble down represents a linear map. So I wrote down a matrix and I fixed some bases. So I decided that the domain space was going to be R2, and I fixed the standard bases. I decided that the codomain space is going to be the linear polynomials, and I fixed some bases. And I just made them up. It doesn't matter. And I'm going to show that the map represented by H with respect to these bases is linear. So of course we know what to do. What do I mean by the map represented by H? Well, the map represented by H takes V, where V's coordinates with respect to the domain basis are C1 and C2, takes V over to W, where these are W's coordinates with respect to the codomain basis. So that's the definition. You write down C1 plus 2C2, 3C1 plus 4C2. That comes from the 1, 2, 3, 4. And then what's H of V? H of V is just simply whatever this number is, C1 plus 2C2, multiplied by the first basis vector, and 3C1 plus 4C2 multiplied by the second basis vector. That's how H is defined to act. We're asking, is that linear? So, of course, the answer is going to be yes. Otherwise, I wouldn't be doing this. So what I have here is that if you follow it through, then 1, 2, 3, 4 acting on a combination gives you the combination of the 1, 2, 3, 4s. 1, 2, 3, 4 acting on a combination, and I just followed it through. I'll let you go through the 1s, the 2s, the 3s, and the 4s, but it's not very hard, is the combination of the 1, 2, 3, 4s. So H on a combination is the combination of the H's. That means that this represents a linear map, that the action of H is linear. Okay, the action of capital H is linear. Okay. So any matrix represents a homomorphism between vector spaces of appropriate dimensions with respect to any pair of bases. What does appropriate dimensions mean? Well, in the previous example, H was a 2 by 2 matrix, so I need to have that the dimension of the domain and the dimension of the codomain are both, they're both 2-dimensional spaces. Okay? And the proof is just a question of going through the previous example and putting in i's and j's. Beta 1s and beta 2s, delta 1s and delta 2 kind of stuff. That's all. All right, and again, the thesis for today is that we can use these representations to figure out facts about the map. You'll remember my finger wagging last time where I tried to make sure that a person is focused on the maps first and the matrices second, the maps first and the representations of those maps second. So what map information can we figure out from the matrix, and that's what we want to figure out today. So we're going to show how to study the map using the associated matrix. It's nice to have it all in one place, and this is the key result, that if you have the matrix representing H, you multiply it by the column vector representing V, then you get the column vector representing H of V. Okay? So this is an instance of that, of the equation star. The first part is about the dimensions. So the 2-row, 3-column matrix has to multiply by a 3-row, 1-column vector, and you got to get a 2-row, 1-column output. So the dimension of H's domain has to be the number of columns in H, because when you represent things in the domain, they have 3 components. And the dimension of H's codomain, little h's codomain, has to be the number of the number of rows here, which of course is the number of rows here. So the fact that we have a 2x3 matrix in this example means that the domain is dimension 3, the codomain, the output space, is dimension 2. So that's just the way the parts combine. Next is an easy one. What about the zero map? Well, the zero map, I'm going to skip the proof and just go to the example here. The argument isn't hard. I'm just simply going to skip it. So the zero map is represented by the zero matrix of the appropriate size, but once you get the bookkeeping right, it's all zeros. So the zero map, for example, from R2 to R3 is represented by the zero matrix. Rank. The rank of a matrix is equal to the rank of any map it represents. So you'll remember that the rank is the dimension of the range. The rank of a map is the dimension of the range. So this says the rank of a matrix, you do Gauss's method and how many rows, non-zero rows remain. That's equal to the rank of the map that it represents. What's the dimension of the range? And I'm going to, as with other ones here, I'm going to do an example. So I'm going to take a linear transformation that sends the 2 tall input AB to the 2 tall output 2A minus B, 2A minus B, and a person can see that the output space is one-dimensional. So the rank of the map is 1. I then went in and represented that map T with respect to some bases. I just made up bases, and I represented, and I got here this matrix. I think you can see, we've done so many Gauss's methods, I think you can see that when you do Gauss's method on that matrix, you're going to get, right, one non-zero row. That the second row is a multiple of the first. Second row is linearly dependent on the first. Okay, so if I represent it with respect to different bases, I get a different matrix, but the same result. Same map, different bases, I get a different matrix, but still, Gauss's method on that matrix will yield one non-zero row. So the rank of the matrix, do Gauss's method, count the number of non-zero rows. The rank of the matrix is equal to the rank of the map. What's the dimension of the range? So if you want to compute the rank of the map, maybe an easy way is to represent the map and do Gauss's method. One-to-one and onto. So if H is a linear map represented by the matrix capital H, then little h is onto if and only if the rank of capital H equals the number of rows. That is to say, the dimension of the range is equal to the dimension of the codomain. And H is one-to-one if and only if the rank of capital H equals the number of its columns. So that's simply because the number of columns is the dimension of H's domain, and the number of rows is the dimension of the codomain. That's all. So just as another example here, so I have the transformation rotating vectors counterclockwise by theta radians, and of course we know that that's 1 to 1 and onto. If you take vectors in the plane and rotate them all by theta radians, why you get a map that is 1 to 1 and onto. And we can see by looking at this matrix, or by looking at this matrix, whichever version you think is simpler, we can see by looking at this matrix that when you do Gauss's method on that, you're going to get 2 non-zero rows. So we get that this map is both 1 to 1 and onto. A linear map that's 1 to 1 and onto is non-singular. You'll remember that we used the word non-singular at the very beginning of the course, and of course there's a connection here. We're going to make the connection here right now. A linear map that's 1 to 1 and onto is non-singular, otherwise you call it singular. That is, a linear map is non-singular if and only if it's an isomorphism. And a non-singular linear map is represented by a square matrix. If you want to be both 1 to 1 and onto, you have to be represented by a square matrix in that case. So, excuse me, it says, a square matrix represents, I had trouble reading the thing. Square matrix represents non-singular maps if and only if it's a non-singular matrix. That is to say, in summary, I can read it over here. A matrix represents isomorphism if and only if it's square and non-singular. So you want to know if your map is an isomorphism. Remember, we did some reasonably complicated calculations in the first section of the third chapter. You want to know if your map is an isomorphism. Here is a strictly computational way, requires no insight. You don't have to do the hard part about ontos. You represent it with respect to some basis for the domain and codomain. You do Gauss's method. Do you have a matrix a square matrix that has no zero rows? Then it's an isomorphism. Okay, and again, I'm going to just in the interest of time, the slides are an introduction really, rather than the whole presentation. The whole presentation's in the book. So of course, I'm going to do an example. So that matrix certainly is square. Does it represent an isomorphism? And the answer, of course, if you do Gauss's method on that matrix, it's obvious that it will have no zero rows. So it represents an isomorphism. With respect to what? With respect to anything. If you fix any domain that you like, got to be two-dimensional domain, or how about the linear polynomials? And any codomain that you like, got to be two-dimensional. So how about the two wide row vectors? You fix any basis for the domain and any basis for the codomain. This matrix represents an isomorphism. Okay. Another example, less kind of dopey. Gauss's method will show you that matrix is singular. That there'll be a zero row. So any map it represents will be a linear map, fair enough, linear, but not an isomorphism. Again, represents with respect to what? What's the domain? What's the codomain? And the answer is any domain, any codomain. Because that matrix is square, I'm talking about a three-dimensional domain and a three-dimensional codomain. I'm talking about any basis for any three-dimensional domain and any basis for any three-dimensional codomain. That will represent a map that's linear, a homomorphism, but not an isomorphism. Okay, linear map, but not an isomorphism. Okay, and then I want to finish off by computing the range space and null space. So I picked a linear map that's again not too easy, not too hard. A function is onto if every codomain member W is the image of at least one domain member V. This function's not onto because there's a restriction. The first component of the output has to be the average of the other two. Do you see that? X is the average of X plus Z and X minus Z. A function's one-to-one if every codomain member W is the image of at most one domain member W. And this function is not one-to-one because the output entries don't use Y at all. So if you hold X and Z constant, let's say you said X equals 5 and Z equals 4, and vary Y, you'll get that many inputs all go to the same output. So we can decide by, thinking it through, one-to-oneness and onto-ness for this function, but the problem is that we're always afraid that we're going to someday, they will be called out by a function that we just can't do hard. We just can't figure it out. No amount of being quick on the draw will suffice to figure out the range space and null space for this kind of, how do we, what's an algorithm? And of course the algorithm involves Gauss's method. Are you shocked and appalled to hear that? So for the calculations, I'm going to use the standard basis just because I could pick another basis, but I'm using the standard basis because it's relatively easy. Here's the action of H on the domains basis, okay, the standard basis, and I got the action of H from right here. And I represented those with respect to the codomains basis. If the codomains basis is the standard basis, then every vector is represented by itself. So that's nice. It saves me a certain amount of work. And that gives me the matrix H. You just drop them down one column next to the other. So here's an example of the calculation of representation of lowercase h, representation of the map, representation of the vector is going to give me, of course, the representation of the application of the map to that vector. And to find the range space, of course, I want to figure out which ABCs can happen. So I do Gauss's method, and I find that some ABCs can happen, but some ABCs cannot. And the restriction is that an ABC can happen if a representation can happen, a representation with A, B, and C can happen, exactly if 0 equals negative 2A plus B plus C. So again, the output representation here, this is a representation with respect to D, is possible exactly if and only if, 0 equals minus 2A plus B plus C. So there's a restriction on which vectors in the output space can happen. It's those vectors whose representation satisfies this condition. So the rank is 2. H is not onto, specifically the range space consists of those W's whose representation satisfies that restriction. To decide if H is one-to-one, you can solve the associated homogeneous system as we have in the past. And of course we get that the associated homogeneous system is you solve x equals 0 and z equals 0, but y can be anything it likes. So H is not one-to-one because the null space is not the trivial space. So the null space is the set of domain vectors whose representation falls in that one-dimensional set. The null space is a subspace of the domain, of course. The null space is a set of domain vectors whose representation has a 0 in the first entry and a 0 in the second entry, but can have anything at all in the middle entry. Okay, and again, back to the 1, 2, 3, 4, because I'm not a very imaginative person, and also because it kind of, is clearly an arbitrary matrix that has not cooked up to be special in any way. And this matrix obviously has rank 2 since the second matrix. The second row is not a multiple of the first. All right, and so we're looking at the equation star, the representation of the map, the representation of the input vector gives you the representation of the output vector. To figure out what is in the range, I do this Gauss's method here. And it turns out that if you give me an A and a B, I can find an associated, way to combine the inputs. So we get that this map is onto. For all codomain vectors A and B, there's an associated domain vector V, namely x is minus 2A plus B, and y is 3/2 A minus 1/2 B. Up here, x is minus 2A plus B, y is 3/2 A minus 1/2 B. So the map is onto, the range space of the map is all of the codomain R squared. And the rank of H is 2. For one-to-one, a person can reason in a number of ways, but for one-to-one, the most straightforward thing to do is to do the homogeneous system by starting off with A and B to be 0. If A and B are 0, you go through all the Gauss's method steps, and you're looking at the only answer is x equals 0, y equals 0. So H is one-to-one, and the null space is a trivial space. There's other ways that a person could reason. A person could also reason, I'll just mention this in passing, a person could also reason that rank plus nullity equals the dimension of the domain. Dimension of the domain is 2, rank is 2, leaves 0 for nullity. So the null space has to be trivial. Also correct way to reason. Nothing wrong with the way I did it. I wanted to illustrate that you can do one Gauss's method here, and then for your null space take A to be 0 and B to be 0 and get sort of a second calculation for free. But there's nothing wrong with the rank and nullity calculation either. Here's an example that isn't square. So suppose I have this for a representation, and I do the calculation that I did on the prior slide, except I do it with this non-square example. For each A and B, there's at least one x, y, z that works. And you can see that the map is onto, since the output space, the codomain space, has dimension 2, because that's the number of rows in the starting matrix. Since the codomain space has dimension 2, the rank of the map, it covers the entire codomain space. That's what onto means. The rank of the map is 2. For each A and B, there's more than one triple x, y, z. So the map is not 1-to-1. You know, if you said it another way, if you take A and B to be 0, you're solving the homogeneous system, then you get 1, 0, minus 3, 0. 0, 1, 2, 0. X and Y are leading, but Z is free. So the null space is got here, you see, the null space has got one free variable, so the nullity is 1. The basis for the null space is the sequence consisting of a single vector, 3, minus 2, 1. So the nullity is 1. So the idea here, ran through a lot of ideas, but the idea here is that we can determine a lot of things about the map by fixing some bases and calculating with the representation. So I'm going to close with an example showing how to extend those calculations to the underlying spaces. So I'm going to fix these three things: a basis for the domain, a basis for the codomain, and a representation of the map. I do the Gauss's method calculation here with the ABCs. The null space is trivial, so H is 1-to-1. If you take A and B and C to be 0, then you get that x equals 0, y equals 0. So the null space is trivial, so H is 1-to-1. The range, on the other hand, contains those output vectors whose representations satisfy that 0 equals A minus 2B plus C. So H is not onto, only some of the codomain space's elements are in the range, namely those whose representations satisfy that, with respect to this basis, satisfy that A minus 2B plus C equals 0. To get the underlying elements of the codomain, you don't want just the representations, you want to know what are the elements of the codomain. So you say to yourself, well, I want to know which elements of the codomain satisfy this property, that A minus 2B plus C equals 0. All right, so satisfy that property, so I put it in. So minus 2B plus C times 1 plus x, B times 1 minus x, and C times x plus x squared, those of course came from right here. And you do the arithmetic, it's not very interesting, and you get B times 3 plus x, C times minus 1 plus x squared. And so the range is actually the span of 3 plus x and minus 1 plus x squared. That's a basis, clearly linearly independent. So the range is of dimension 2 with this for a basis. So I can figure out not just the representations of members of the range, but I can actually figure out the range. So I can figure out things about the underlying space as well as about the representations. Okay, very good. A lot today, but nonetheless also a lot learned today. So this business of representing the function with respect to bases and looking at what that representation has to tell us proves to be very fruitful. Okay, so very good. See you next time.